Not really that fun, by the way. Hello, everyone. Thank you for braving it out in this horrendous weather to be here today. And welcome to the Geological Society, both to those in the room, and it's fantastic to see so many people here in this lecture theatre, and to those online, welcome. A few housekeeping items before we begin. I'm afraid we do have a few housekeeping items today. Firstly, there has not been a fire alarm scheduled, so if the fire alarm rings, please treat it as real. Make your way out using the designated fire exits. So that means if you're towards the front, behind this curtain is not the Wizard of Oz, that's actually a secret little passage through to the courtyard, which we're only allowed to use if there's a fire. So that's very exciting. Otherwise, if you're sort of nearer the back, there's 3 exits there, and then you can either go onto Piccadilly or through the fire exit on that direction into the courtyard, and we congregate just outside the Royal Astronomical Society. There'll be a question and answer after the talk. Those people who are here in person, if you have a question, could you please raise your hand, and somebody will come round with a microphone. It is helpful to wait until you have the microphone because that means the people online will be able to hear the question. Those online, please post your question using the Q&A function, and your question will be read out loud and answered. I would like to thank KSAT, Kongsberg Satellite Services. They have sponsored this series of public lectures. It's thanks to them that we're able to have a drinks reception afterwards, so that is most welcome. And that will be taking place after the talk in the room behind us in the lower library until 8 o'clock. Now, the other bit of housekeeping is that prior to this evening's public lecture, I'd like to quickly let you know about some changes to the Geological Society's bylaws. Absolutely fascinating. I'm sure this is the main reason that you're here tonight. But the bylaws are essentially the rules by which we operate. And as some of you will know, there's been a consultation exercise and a review of our bylaws and Royal Charter over the past 3 years. Now, we have some proposed redrafts of these documents. The new documents essentially bring our rules up to date with current charity law and regulations and modern best practice. Now, why am I telling you this, you may ask? Well, our current bylaws, which are quite old, require us to make an announcement at 2 consecutive society meetings if there's any proposed change to them. So this is about a bit like reading banns at a wedding, and that's what I'm essentially doing now. So as this is a meeting of the Geological Society, I'm letting you know about the proposed changes. If you're a fellow, you will be invited to vote on them later in the summer, and there'll also be a special general meeting in the autumn to hopefully confirm the changes. So this proposal is to amend the Society's bylaws and Royal Charter, and all the information regarding the proposed new draft can be found. Either there's one of those little codes that you can scan just on the reception, the desk outside, or you can go to our website, www.geolsoc.org.uk/bylaws. Right, now on to the main item. I'd like to introduce Heather Handley, who we're lucky to have as our speaker this evening. Heather is an associate professor of volcanic hazards and geoscience communication at the University of Twente. I think I've pronounced that right, hopefully, in the Netherlands, and an adjunct associate professor at Monash University in Melbourne, Australia. Among many other things, she is director of the Earth Futures Festival, which is a UNESCO-supported international geoscience film festival, which Heather co-founded. She's co-founder and inaugural president of the Women in Earth and Environmental Sciences Australia Network. She regularly presents and appears in the media talking about volcanoes. She's featured in a number of TV documentaries and is writing an upcoming book on Australia's geological and cultural volcanic heritage. She was awarded this year's European Geosciences Union Katja and Morris Craft Award. In 2020, she received the Geological Society of Australia's Beryl Nasher Award, and she is a Science and Technology 2021 to 2022 Australia Superstar of STEM, among various other awards, which if I keep reading them out, we won't be able to get started. So Heather has a geology degree from the University of Edinburgh, a PhD in volcano chemistry from Durham University. So please join me in welcoming Heather to the stage for what promises to be a fascinating lecture, Forged by Fire, How Volcanoes Shape Our Landscapes, Law and Lives.
Thanks very much. So before I start, I'd like to acknowledge the traditional custodians of the many lands where this research was carried out and where the stories that are told took place. And I pay my respects to elders past, present, and future. So for around 3.6 million years, humans and our early ancestors have had an extraordinary relationship with volcanoes. As you can see here, recorded by footprints walking across volcanic ash in Tanzania. Now, these footprints they were not running, they were walking at a leisurely pace. It appears that these people were very familiar with volcanic ash falling around them. They were not scared by it. And interestingly, there are 2 prints in the larger one. So one was following in the footsteps of another, suggesting maybe it didn't like the feeling of the wet, sticky mud under its feet. But ever since this time to present day, humans have been fascinated by volcanoes. I know my life has been pretty much determined by them. And you can see here, as recently as 2021, the eruption in Iceland, which is still relatively ongoing. And this attracted around 356,000 visitors to go see it. So we can see we're still fascinated by volcanoes. So they shape our landscape. They obviously give us mountains, they give us calderas and lakes, they give us water resources. So lava flows often take the path of least resistance and flow down the river valleys. They might then form swamps where they do dams and waterlogs. We know that they shape the weather, so these eruptions can affect the climate. They caused the year without the summer after the Tambora eruption in 1815. And from the lava, from the deposits, they weather to give us very fertile soils for agriculture, but also that control and shape biodiversity, whether this is lava caves that have endemic species, or it's isolated volcanic maar lakes that have particular endemic fish in them. So they really shape this. They are the ground that biodiversity builds up upon. They, of course, give us the geological resources that we need, so that have all shaped through the past, from obsidian that's been used in tools, to basalts that's been put down as ballast and as aggregate on our railways and used in our buildings. So, and also for geothermal. So there's a strong potential for geothermal. And so these deposits also, importantly for geologists, give us perspective. These are time capsules into the Earth's history. So where we do get these exposures, you can see we get these layers upon the Earth, and we can study those as geologists to understand the history of the Earth. But they also shape culture, and this is one of the things as a geoscientist I'm becoming more and more interested in, is this relationship of volcanoes with society, because I also believe it's a very useful way to communicate to people and get them interested in learning more about volcanoes and geoscience and hazards and risk. And so over cultures for many millennia, volcanoes have formed sacred sites. They're sometimes recorded within place names, and lots of oral traditions have been created around observed volcanic eruptions or creation stories about these volcanic landforms. And some of those traditions have then led to cultural adaptation. So in the way of, it might be that those landscapes have been utilized, so the lava, the rocks, into landforms. And here is a lava flow in Australia. It's about 37,000 years old at Budge Bim. And the lava went down the river valley, as you can see there behind, and it blocked and formed this swampy landscape, which was then turned into an aquaculture site around 6,000 years ago. And it was used for collecting and harvesting eels. So there was a whole aquaculture system built upon this lava surroundings. So very important site, and now it's a World Heritage Cultural Landscape. So we know that you can use these materials to build things. So the lava goes on the ground, and then we raise it up into constructions. So when you go to some countries, you can see that the buildings and the feel of that city or that place is very much determined by its geology, and volcanic rocks obviously are part of that. And then finally, the influence on arts and literature. So there's many cases of stories about volcanoes, lots of artwork, and we'll see some examples of that a bit later in the talk. And then the last part is that they shape our lives. So it's one of the, I guess, key messages that I want to get across today is just how much, in unexpected ways or in unexpected places, volcanoes do play a significant part of our lives and shape history. There is, of course, a risk of living near volcanoes. They do give us the fertile grounds. They're great for agriculture, but living near volcanoes obviously comes with some risk. In terms of human history, this is a picture. I was lucky enough to go to Herculaneum, and you can walk down through where they've excavated around 25 meters of volcanic deposits that buried Herculaneum, the Roman settlement. And this was the former shoreline before the eruption occurred. So this was where a lot of people were waiting in here, waiting for boats to escape the eruption that was coming, but sadly they couldn't. But these volcanoes, they can be very destructive. They cause disruptions to civilization, but they also give them these snapshots into historic moments in the past, where they preserve these time capsules of past human life that we can excavate and analyze today. And then one important part is leisure and tourism. So I don't know who's been to see a volcano on holiday, but I have now been banned by my children to stop taking them to volcanoes on holiday. So I did manage to sneak in Lanzarote by showing them a picture of the beach and the swimming pool first. But yeah, there's a very important part, and obviously that also comes with some risk if you go into active volcanic places. So whether or not you live in an active volcanic country, it's also useful to know a little bit about volcanoes and volcanic risk. So with increasing number of people on the planet, more and more people are living close to volcanoes. And it's now estimated that there's nearly 1 billion people that live close to, that's within 100 kilometers of an active volcano. There are some large cities as well that are built upon active volcanic fields, which I'll explain a bit more shortly, such as Auckland, Mexico City, and Melbourne, which we'll get onto in a moment. So this led me to think a bit more about how can we better understand volcanoes and their hazards. how can we understand more about what warning timeframes we might get of future volcanic eruptions? And then how can we better prepare for that? So how can we look beyond the areas that we usually do to understand things to really improve and prepare and reduce volcanic risk at both local and at global levels? So there might be a little bit unexpected, might have been given away a little bit in the hint of the area of my focus, but I'm going to today take you to see, as a case study, I want to take you to a place that you might be the last place you think of when you think of volcanoes, and that's Australia. So when you think of Australia, kangaroos, a dusty red outback, might be beaches, might be some scary animals, but actually I'm hopefully going to show today that even in Australia, volcanoes have been absolutely fundamental in every stage of human history and development, and have controlled a lot of the natural environment too. So it's not surprising that you might not think about Australia as a volcanic area, because most of the volcanoes that we see, active volcanoes on the planet, are formed at tectonic plate boundaries. So this is where we have the edges of these large chunks of the earth made up of the crust and the upper part and the upper mantle. So you can see that where we've got these red lines and all of these volcanoes, they're typically where tectonic plates either collide together, such as at subduction zones like Indonesia, they pull apart like at the Mid-Atlantic Ridge, or we might get these anomalous areas like in Hawaii, where you can see in the middle of the Pacific, in the middle of the plate, we've got volcanic eruptions there, which are related to enormously hot mantle plumes upwelling. So in the middle of the plate, we call them intraplate volcanoes. And you can see Australia there sits in an intraplate setting. And you can also see it's got just two, but it's got two red triangles. And these are the Holocene eruptions. So there was actually one on the map. I had to add the other one manually. But there are now two confirmed Holocene eruptions. So this means since the last ice age, so around in the last 11,000 years, which for geological timescales is very recent. So the area is still considered active. So since the demise of the dinosaurs around 66 million years ago, Australia has had a whole lot of volcanic activity down its eastern margin. So all of these red, yellow, purple, I think orange, these are all Cenozoic volcanic areas. And the two youngest areas that are still considered to be active, that were those red triangles on the previous slide, are found both in the northeast of the country and the southeast. So here, eruptions in the Newer Volcanics province are around 5,000 years ago. And in the McBride, up at the top, it's about 7,000 years ago, plus or minus 2. So you can see these are very recently active areas, geologically speaking, and areas, because they've erupted in the Holocene, volcanologists believe that they have potential for future eruptions, which is where I guess I've become really interested in Australia's volcanoes. If we focus in on the Newer Volcanics province, you can see what these volcanic fields look like. So they're not a typical pointy volcano where there's only one volcano in that area. These fields are huge areas that consist of multiple small, usually short-lived, small amounts of magma, and they pop up in a random fashion, like a game of whack-a-mole, which I'm missing from the part there. So it's very hard to understand where the next eruption is going to happen, when it's going to happen, and some of these fields, so for the New Volcanic Province, it's been active for the last 4.5 million years at least, with the last eruption only 5,000 years ago. The other factor in these areas, because they are small bits of magma usually coming up in new places, if they come up through a groundwater system, a lake, or interact with any water of any kind, then that can obviously lead to an explosive reaction. It's akin to, don't try this at home, if you put hot cooking oil and cold water together, you can imagine that the reaction you're going to get. So the style, even though it's typically otherwise would be very effusive, meaning very gentle, if you get situations where you can see these yellow and blue, this is a lot where the aquifers are, as well as over where you can see I've got the Mount Gambier. These are areas where there are aquifers, and this leads to these explosively formed volcanic eruptions. So the black triangles are areas that I'm going to show some examples from today. You can see that the field sits on the edge of Melbourne. So most of the activity has happened away from it, but future activity, especially with the wind direction, can also carry ash over Melbourne. And it's been worked out that Mount Gambier, we measure volcanic eruptions on a volcanic explosivity index, which usually runs from 0, which would be like a Hawaii lava flow you could walk away from, to 8, which would be a super volcanic eruption. So the Mount Gambier eruption actually sits somewhere in the middle of EI4, which is akin to the Icelandic Eyjafjallajökull eruption that, as many of you would know here, ground plains across Europe. So this is another reason why I've become really interested in this, future potential eruptions that could then, in theory, that one would take ash all the way across to New Zealand and to Auckland if it erupted at the same, if there was another eruption at that scale. So in my research, I'm traditionally trained as a volcano geochemist and mineralogy petrology. Over time, I guess my interests have broadened, and I've really come to see the value of incorporating or considering broader sources of knowledge, especially more than just the geological. So some of the things that I hope to take you through today is to look at some of the geological knowledge that's helping us understand about warning timeframes. So that's what I'm really going to focus on today, is about how much warning might we have of a future eruption if one occurs in these intraplate volcanic fields. Then I want to try and look at cultural knowledge. Is there anything that we can gain? And this is why Australia is a brilliant place for this. It's been relatively isolated since humans occupied for about 65,000 years until colonization 250 so years ago. So there are lots of long-lived oral traditions about the environment, about nature, and about volcanoes. So what can we gain from that? Is there any insight we can get about impacts on environment and people from these oral traditions that no one has seen an eruption, obviously, in 5,000 years? But also want to look at other types of knowledge. So won't have too much time to go through these today, but I'm also looking at archaeological, paleontological, and also working with social sciences to do surveys about what do people think at the present, what are their perceptions, and also how do we communicate this and how better can we communicate about volcanoes in this region. So if we look at geological knowledge, so the first thing when we go in the field is that we have great insight into how these volcanoes, how they happened, how they evolved by looking at the deposits. So you can see at the bottom here, this is a exposure at Mount Norak in the New Volcanics province. And you can see at the bottom, it's cream colored, it's quite bedded, it's quite, there's obviously a dip there where that big lava bomb's fallen in, and it's very fine grained. Now this part is then, from geological interpretation, what we call a phreatomagmatic, so water and magma. So this is our magma coming up, interacting with the groundwater, causing an explosive, fragmenting it into tiny pieces, pyroclastic surges, these very fast, powerful blasts that go across the landscape. And then you see there's a transition, and you see this kind of coarser, there's larger, it's darker. These are our lapilli. This is from a more scoriaceous, more strombolian type of eruption with these lava bombs that are then landing inside. So from this, we can see that there doesn't appear to be much gap, like there's no soil in between, probably happened quite closely in time. So we can see that we might have a very dynamic setting based on the availability of the maybe external water. So maybe the magma comes up at first, then it kind of just uses up that water because it's heated it, it's turned it into steam, and then you've got this more magmatic where it's coming straight through and not interacting. So we have a change of hazard, a change of style, and a change of landform that's formed throughout this eruption. And if we focus in on the lava bomb, you saw there were some little green specks in there. These are actually parts of, these are mantle xenoliths. So these are peridotite, spinel peridotite. So we know that they come from anywhere from the base of the crust. They come from the upper mantle down to about 70 kilometers where spinel is stable. So these green chunks have been carried up by the magma and erupted out of the volcano. Now, why is that interesting? Well, for a few reasons. One, it shows that there must be direct pathways from the mantle straight through the crust to the surface. Otherwise, you wouldn't be able to get these big chunks out at the surface, they would be kind of blocked, or like, you know, they would just could not get up. So that suggests that we've got what we have dikes, and we've got these probably open pathways for magma to come to the surface fairly quickly. The other point is that these mantle peridotite xenoliths, so they are denser than the magma. So they're very heavy. And I know that because I brought 41 boxes of rocks with me, and the removalists were really struggling with the weight of the boxes because they were full of mantle xenoliths. So they're much denser, they're heavier, and it's harder for the magma to carry up compared to crystals. So the other thing it tells us that the magma had to move fast. So if you imagine you have a cylinder of honey, you drop a pebble in the top, the pebble's going to slowly sink down because it's more dense. So you have to move the magma, and you have to move it at a certain speed to make sure that that can keep coming up without settling down. So what we can do, so working with Tom England, who's a master's project, we went to Queensland. So there's more volcanoes in that active area in the northeast. And we went to the Neovolcanics province, and we had a look at the mantle xenoliths we could find. So he had a look at over 100, and we were a little bit biased. We tried to find the largest xenoliths because that would then give us the fastest ascent times, and what we're concerned about is the warning time frames. And then, so from that, there are some assumptions that you have to make. So we assumed that it just transported all in one go. It didn't kind of stop-start on the way. We had to assume, based on the model that we used, that they were round. And you can see from the last photo that they're not. So in future, we're hoping to improve that model to take more realistic shapes and dimensions. And so we just took a 50-kilometer depth we know it's anywhere between, say, 35 and 70. So we just said, okay, if we move one from 50 kilometers depth of the size that we see in a kind of a honey-like magma, we can see that the maximum xenolith size we had was 25 centimeters. Here it's the radius, so it plots there. And what that told us, it gave us an estimate of how fast we would have to move it to avoid this kind of settling rate based on the density of the material on the size. And so what that told us, that you'd have to move as fast for the one this size to go from 50 kilometers to the surface, it would only take about 50 hours. So, you know, you're only looking at just over 2 days. So if you're moving magma from the upper mantle to the surface, and that whole process on average takes just 2 days, this is your warning time frame. You're not going to have very much time that you're going to see earthquakes or have much warning or be able to evacuate. And we know that in these aquifer settings, they can cause these very quite explosive with these pyroclastic surge-like hazards. So do we see the same thing if we look at the minerals and the volcanic crystals in the rock? Well, what we can do is we can take a very thin slices of rocks. So if you imagine that a human hair is about 70 microns in thickness, these slices are about 30 microns in thickness, so super thin slices of rock that we can look down the light microscope, and we can also get some really nice close-up pictures on the scanning electron microscope. And what do we see if we look on the scanning electron microscope? So this is now looking at volcanic rocks from Mount Gambier, the youngest volcano in Australia. And we can see that in olivine, if we just focus on that one, we see a wide range of olivine types. So we've got different shapes. We've got these very skeletal looking ones that look like skeletons in the top middle. You can tell by the grayscale about the magnesium content, and that can tell us about changing environments, different environments that these crystals grew in. So what we tried to do, and this is work in progress, is we're now trying to build a picture of what types of shapes of crystals have we got, what can that tell us about how magma moves to the surface, and also the composition. So the different colors of gray relate to the magnesium, so that can tell us a bit more about the different environments that these crystals grew in. So where you get a dark rim, that suggests that that crystal entered a more magnesium-rich, so a more primitive type magma. And where you get this normal rim, which in this one here is a mantle xenocryst. So you imagine you had that big green chunk of mantle rock, and you break off a little crystal at some point on its ascent. Then it reacts with the magma around it and grows this lower magnesium rim because that's what it sat in. And so you can end up with this feature. So the key is then to analyze them, try to work out where did these crystals come from, what pressure, so the depth, what temperature did they form at, which we can get from the chemistry to build a picture. And so from the shapes of the crystals, so I mentioned we have these skeletal ones, there's experimental work that looks at the shapes that you get of olivines, and then that relates it to how fast you have to cool, how much you cool, and how fast you cool. So where we get our skeletal, you can see on the top right, then you're cooling a moderate amount and quite quickly, but not as quickly as if you get these dendritic features. So if you see dendritic features in the crystals, that means you've cooled really, really quickly and you've cooled by a lot. And if you get the skeletal or the hopper, then that's kind of more intermediate. So what we can do is build this picture up. And if you imagine we said, we know we have these physical chunks that have come to the surface. We know we have open pathways. So we've probably got these dikes, so like sheet-like transport of magma. And that may cool quite quickly because you're suddenly cracking in the rock. And that's a cold environment compared to, say, it being traveling in a, it's got to push through a new area. So it's actually a quite cold pathway. So it's trying to unravel all of these things together to look at how does the magma ascend, how fast does it ascend, and what can we build a picture about the plumbing system beneath the volcano. And this is just some work that's also in progress. So here focused on one of these xenocrysts, so foreign crystals that's come from the mantle that ended up inside the magma, moved to the surface. And if you go back to Chiara's talk from April, she did a lot of, explained a lot about diffusion, how we can use chemistry, the profiles across these differences in chemistry to work out timescales of magma ascent. And so what the next step is to look at these profiles across and try to work out what's the time frame from the mineral scale. We've got the hot, this big chunk. We had an estimate of the time frame. How well does that compare to actually what we see when we do diffusion chronology in actual volcanic crystals? So if we move on to traditional knowledge, local knowledge, or long-lived knowledge has been really important to give insights into environmental changes and past natural events. And environmental changes, so after the last ice age in Australia, there was coastal flooding, and there's now been at least 27 recorded points all around the country in oral traditions of this coastal flooding. So this is memories that are very long-lived. You're talking at least 7,000 years, at least 250 generations that have passed on these stories and these memories. And we see the really important value of traditional knowledge in disaster risk reduction. And this is an example from the 2004 Indian Ocean tsunami. So the Moken people, who now kind of occupy the Soin Islands near Thailand and Myanmar, they had an oral tradition about the laboon, which is the big wave that eats people. And it said it was passed on through generations, and it was told that that is a cleansing wave, but it's very destructive. If the sea recedes out, then they have to get to higher ground, and that this wave only comes once every other generation. So this story actually saved lives, and also in another place in this one of the islands closer to the epicenter of the earthquake, also had traditional knowledge from 100 years ago that really helped save many lives and respond quickly, and more quickly than you would to a tsunami warning system. And so, unfortunately, slightly different story. So during the Krakatoa eruption in 1883, in Australia at that time, it was post-colonial, so there's European settlers there. They had little awareness about tsunami warnings, and so when they saw the tide going out, they were talking about booming noises and an unusual receding of the tide. Everybody on the beach in Western Australia went down onto the beach because then all the fish were floundering on the beach. They went to go harvest. They went actually out towards the ocean to collect all the fish. And then, of course, there was this big onrush of a wave. Luckily, I didn't hear about any human fatalities, but there were 10, I think, rams or stuffed sheep or something like that that were lost, that fell off a platform going onto a boat. So you can see the difference when you're not using that traditional knowledge, when you're not using that long-lived and learnt knowledge, that it can actually lead to fatal results. So it's trying to say, how can we better integrate modern science, modern volcanology with traditional knowledge, and to learn more and prepare better? So in Australia, there's been, since human arrival around 65,000 years ago, from the data available of the volcanoes we know, there's been about 15 eruptions that have occurred. And there's also cases, so this is Tower Hill, and in the Neovolcanics province, it's about 37,000 years old, and there's been an axe, the Bushfield axe, that's been found beneath the deposits in here. So that shows also that people were living in this landscape when the volcano erupted. And the memories of many of the volcanoes are captured in these oral histories and have been passed on. Now, unfortunately, because of the history of what happened, and I'll show an example of where volcanoes played a role in this colonial conflict with Aboriginal people upon settlement, that many of were recorded, these oral traditions were actually recorded by colonists, and we can access them through these literature. But obviously you have to think about how they were recorded at the time. There are many accounts where they said they try not to put any bias or any interpretation and record them as they were told. But of course, you know, it's based on the time that these were recorded. And there's also potential bias that I'm trying to work with Indigenous knowledge holders, but there's also potential that with my agenda as a volcanologist, I'm looking for particular aspects in volcanic stories. It's possible that I can also misinterpret or overinterpret or analyze them out of context. And so there's obviously limitations and challenges with working with traditional knowledge, but hopefully we can be aware of those things. So what can these oral traditions tell us? Well, they can tell us a range of things. And so the examples, there's two examples I'm going to show. One is that it tells us about relative timing of events. And then the other example is going to tell us something about pre-eruption, warning times, and how an eruption unfolded. So the first one is for Mount Gambier. So you can see here it's a Mar complex. So this was Australia's youngest volcano, but we don't necessarily know that. There's another volcano, Mount Schank, which is actually one of my favorite volcanoes in Australia. And these two erupted probably very closely in time. The age dates we've got from various different absolute and dating methods do vary depending on which technique you use. So it's not really been that clear what is the actual date and the how, which one actually was first, which one claims the title of Australia's youngest volcano. But there is an oral tradition associated with the eruption chronologies at these volcanoes. So there's the Boandic people of around Mount Gambier have a traditional story about a giant ancestor called the Crate Bull. And he lived for a long time, quite happily. They were collecting roots and making an oven at Mount Muirhead, which is the older one on the left there. And then there was one night when they were sleeping, there was a name of the sound of a bird they called the bullin that shrieked and woke them up. So they fled to Mount Schank, where they thought they would be safe. They carried on, continued to gather food and cook. And one night when the oven was empty, the voice of the bird occurred again. And then they fled further inland, thinking that they would be safer inland, and ended up at Mount Gambier, where unfortunately they camped for a long time, but then the water came up and it put out the ovens. And so from the oral tradition, we can infer that that Mount Gambier would be the most recent volcanic eruption. We're still yet with the science, so what we can tell from the magnetics that they've done on the rocks. So when these magnetic minerals in the rocks after eruption, they get frozen in a particular direction. From that, they think that the eruptions were about 300 years apart, but it's not possible to tell which one came first. And the relative stratigraphy, still, from what we know at the moment, hasn't been able to tell this. So in this case, we believe that the oral tradition really can give us that insight into relative timing that we can't get through the scientific dating at present. And the second example is now from Northeast Queensland. So this is at Lake Eacham or Yiddiam. And here there's an oral tradition about, it was just after some young people had been initiated and they were at the camp, and they were told to stay put while one of the elders went out to look for food. While he was out looking for food, it unexpectedly got dark, and he started to think, oh, what's going on here? There must have been some trouble back at the camp. So as he went back, there was a cloud getting higher in the sky and yellower, and there was a very strong wind blowing, and a cold wind. he saw water rushing up and engulfing everything. And then the animals came running, partly blown by the wind. The old man tried to cut and hit the ground, but it was no use. Through fire, but the water came up and the people were gone. So this is a Mar volcano. So this is one of the volcanoes that we know is an explosive ash-producing volcanic eruption. The story marries well with what we know from the volcanological record about the types of events that you would see from a Mar-forming volcanic eruption. But importantly, what it says is that there was very little warning. So the people were camped, they were not fleeing. And interestingly, the animals were also only suggested to have moved after the eruption began. So it suggests that there is very little precursory activity that could have warned them about this ensuing volcanic eruption. And if you imagine these things happen in, in areas where there's not been an eruption before, then it's quite likely that there weren't very many signs beforehand. And one thing that came apparent from a pollen analysis in the, I think it was in the late 1960s or early 1970s, was that showed it was on a nearby, another volcanic crater lake, Uramu. And there it showed that the rainforest that we see today and the landscape has only been there for around 8,000 years. The tradition talks about the scrubland. So in the tradition, they mention the vegetation is scrub, not rainforest. So that also shows that these stories, the traditions, you can combine the science with the oral tradition to really build a picture of what the landscape was, what the environment was at the time. The tradition also talks about bare land. It talks about, in the several different versions where it talks about the bare land as if there's some importance of stressing that it was bare. And so for me, as a volcanologist, my interpretation could be that there were some diffuse gas coming up that was enough to kind of kill the vegetation, but not necessarily for people to notice that anything was happening. So, you can interpret, you can overinterpret, but, you can also look for signs that there are. And so when you put things together, we've got the insight from these large chunks of the mantle that suggests you have to move fast to get them to the surface. There have to be open pathways. I've got the mineral data, which I need to work on to find that out too. But from the traditional knowledge, it does suggest that there was also very little warning, at least for the Mar-forming volcano in Lake Eacham. We can also look to historic events that we know in different places around the world where we've had these small volcanoes in interplate settings, or at least monogenetic, meaning single formation, these small batch eruptions. So in 1997, there were two Mar-forming eruptions in Alaska. They took place in very short succession of each other, and they were very short eruptions. I think both were over within about 10 days. The area was not well monitored, obviously, because it's quite remote, but there were no precursory signs or not much detected in terms of earthquakes, which also supports that you can get these eruptions without very little warning. The other one is more of a scoria cone forming eruption, so the one at Paracutin in Mexico, famous for forming in the cornfield of a farmer. There were earthquakes detected in the neighboring area for about a few weeks beforehand. And then the eruption lasted there for, I think, about nine years. So quite different, even though we could expect these types of volcanic eruptions in interplate volcanic fields. It shows you there could be a spectrum of warning timeframes associated with future eruptions. So we know it could happen quite fast. What about the Australian public? How prepared are they for the next volcanic eruption? There is currently no emergency management plan for internal or external volcanic eruptions in Australia. And you can see here that only 4% agreed that Australia were well prepared for dealing with volcanic eruptions, and only 6% were aware of any emergency management plans or warning systems for volcanic hazards. And considering this survey goes out through my networks as well, I have got the record of what kind of background people have got, and there were some, I guess, more geoscientist type people answering this. So one interesting comment was made, if there was a volcanic eruption, I would have no clue what to do, where to go, or who to ask. When asked if there were parts of Australia that were volcanically active, most people neither agreed or disagreed, somewhat disagreed, or strongly disagreed. So somewhat work to be done there. But of course, the geoscientists, you think, would have a clear message, would be all on the same page, but no. So I've color coded these, so the green on the left to the red on the right. So one geoscientist said there's no active volcanoes on the Australian continent. However, if you're a time traveler and land in Australia in 5,000 years, you better watch out. So basically just fobbing this off through to an emeritus professor at ANU who said an eruption could hit Melbourne at any moment. In terms of Melbourne and Auckland, there's every chance another volcano could blow. You could see lava flowing down one of the main streets in Melbourne. So you can see the messages, and in the middle it's kind of I guess a bit more neutral, just saying we need to prepare and we need to know a bit more. But you can see the message, there's no information going out to the people that's very consistent. And I think that's a problem that we also need to work on as a geoscience community, is that when we do give information, it's at least consistent within the community that's talking to the media. So what can we do? Well, I think volcano geoheritage, so it's not really where I started off my career, but I think it's the direction that I'm heading in. I'm just absolutely amazed with the role that volcanoes have played. I've been researching now for the last 4.5 years, writing a book, hopefully it will be finished soon, on this role that Australian volcanoes have played in human history and on people. And everywhere you look, you find volcanoes, which to me was very surprising. So whether it's your drinking water resource for the local town, it's for going for a swim or cool off on a hot Australian summer day, or it's the lives of your family and the history of the mining and the building of the cities, the foundation of the cities. There's just so much everywhere you look to say that they're really entwined and this thread that weaves through the Australian history. So not only are they controlling the natural landscape, and here's a really nice example. So this is a lava flow deposit in the New Volcanic Province. You can see very clearly the edge of this lava flow. His picture I took, where it's just, you can see more end on what these look like. So these are called the stony rises. And they displace the water. So you can see that the drainage channels, they've had this impact on the streams, the creeks. So you can see this drainage channel that goes around the edge, it's been displaced. The topography of the land means that there's different flora, which means there's different fauna on the stony rises versus now what has become very rich agricultural land. And there's cultural influence too. So around the edge, you can see that there's a dry stone wall. So obviously when you've got these stony rises, you've got a large amount of loose blocks. These blocks were then used to build initially squatting walls for colonists to advance into Aboriginal lands. And so these walls then also separated the pasture lands where the cows were from where the sheep were on the more rocky land. And so there's a whole history, there's a whole story, even in just one locality, that can really tell some of the history, which I think is just a great way to contact, communicate, and talk to the public and get them interested. You know, we know that humans are only interested really in other humans. And I know Ian Stewart, probably, I don't know if he said it last month, but geologists are quite unusual in that sense, that they're really interested in rocks and not just other humans. But one of the problems we have is in conservation. So obviously we have this volcanic geoheritage. It's very useful for us. We like to quarry it. We like to use it. My house in Sydney had a scoria path around it. I used to think, oh gosh, which volcanoes had to be destroyed to actually put that there. But you can see they're very useful for us, but it's got to be a balance. So conservation, preservation, as geologists, we also need a nice quarry face to be able to see the section through the history of the volcanoes, but there has to be some balance between destruction and conservation, and obviously working with different landholders, indigenous peoples, and is obviously can be very challenging to balance all these land uses that you want. So quarrying is a big one. Urban advancement. So in the New Volcanic Province, outside of Melbourne, advancing into the volcanic grasslands has really been detrimental to these unique, it's actually an endangered ecosystem. There's lots of endangered endemic species. So there's an earless dragon, there's a legless lizard, and there's a plains wanderer bird. It sounds a bit like the beginning of a joke, but yeah, they're really seriously endangered and threatened because of the destruction and the advancement. And not only that, so renewable energy projects. So there's a lot now of cases where Wind turbines are being put on higher areas. That's often the volcanic cones. And so there are wind farms across the volcanic areas in the new volcanic province. So it's always got to be this balance of what we need and what the destruction is, and the destruction of the geoheritage. And so the one thing I really would like to emphasize is that there's so many stories to tell. There's so many ways we've interacted with these landscapes. And this is an Austrian-born 19th century artist, Eugene von Gerard. He was a traveling artist. He recorded a lot of the volcanic landscapes. And it was a time when Alexander von Humboldt had told all these artists to go off and record in great detail the nature. You know, these were great resources about the vegetation, about the natural environment. And so there's a brilliant resource that we have. And I was lucky enough in Sydney to go to the State Library and hold his original sketchbooks in my hand and look through the pages. But not only is it just to appreciate the art, you can see how he structured it, how he has portrayed the person, which I presume is a European holding a gun, looking like they're anticipating to enter into these stony rises. Now, these stony rises were very important in the resistance of the Aboriginal peoples, at least in the new volcanic province. So for the Gunjik Mara people, they resisted colonial advance much longer. And I don't know if you've ever heard of the Umarella War. It went for at least a decade. It was around the late 1830s to early 1840s where it was most violent. But the Aboriginal people resisted the longest in these areas because they could go and hide in the stony rises. So the multiple stony rises across that area. So they would be able to go make their attacks and retreat back to these lava flows. So they played, and it was impossible then for people to go and chase them. They couldn't go on horseback into these areas, and it was hard to go by foot, so nearly impenetrable for the horses. So these stony rises obviously have a history. It can be a very difficult history in some cases, especially for Australia. But what they can also do is open up a communication about reconciliation, about difficult conversations about the past history of Australia. And there are multiple examples where Australian lava flows, volcanic landforms, whether it's caves, whether it's walls like this of lava, have played, or whether it's just physically rock material to throw at colonial advance in Queensland. And so there's a really strong history of interaction with volcanic landscapes in all aspects of Australian history. So if we move out a little bit broader, people in Australia might not necessarily be too fussed about an eruption in Australia, but we also have to remember that anywhere in the world can be subject to impacts and hazards from volcanic eruptions. And so in historic times, cross-border eruptions, so eruptions that have occurred outside of Australia that have impacted Australia, have come from different countries: Indonesia, Chile, New Zealand, the Kingdom of Tonga being a fairly recent one that also affected different places in the world. There was an oil spill in Peru. I think 2 people passed away in Peru. The beaches were closed in Australia. There was a warning and evacuations in Japan, and the noise was heard as far as Alaska. So lots of countries can be impacted. And so one other message is that we are very poorly prepared, I believe, and other researchers believe, for the next larger scale volcanic eruption. We saw how the memory of COVID just 100 years prior, in a technology-dependent, more populated world with complicated transport and global transport systems, was impacted in a way that we probably never expected. And it would be the same with the next larger scale volcanic eruption. So not the largest, not a super volcanic eruption, which might only happen on hundreds of tens, thousands of years, but something that happens slightly smaller, but like a Tambora, which is a volcanic explosivity scale of 7. So the last one was in 1815, caused the year without the summer, the following year. And the other aspect is that we've got not only this global implication of future larger scale eruption. So in usually a Tambora scale eruption happens, we get 1 or 2 every 1,000 years. In the Asia Pacific, it's about 1 every 400 years. But what we've also got now is a change in climate. So we've got ice melting in volcanic areas, which can reduce pressure, change crustal structure, can also, as been shown in Iceland in the past, to cause more melting through decompression melting, which means there's lower pressure, so it melts more. There's increased rainfall, so we're seeing obviously a lot more moisture, getting increased rainfall. There's been cases of rainfall triggered volcanic eruptions where you have, so in Indonesia there was one, you've got this dome, like a lava plug at the top, which is quite unstable, and it got destabilized by a rainfall event. So this makes it very hard in monitoring to be able to, at the moment, predict when these things are going to happen. What are we doing for time? I'm nearly there. Rising sea levels is another one. If you imagine you've got a lot of volcanic islands, there's lots of volcanic islands in subduction zone areas, and sea level rise, where are the people going to go? They're going to have to move closer to the higher ground, which is going to be usually closer to the volcanic vent. And then we've got a change in atmospheric structure. So with the changing climate, how volcanoes interact with the atmosphere is also changing. So in the future, it might be that a larger volcanic eruption can move faster around the world. And it might mean that actually a smaller volcanic eruption has less impact on the climate, because the position of the tropopause is changing, and some of the air currents are changing too. So there's still a lot of research in lots of areas of volcanology and related topics. And so just wanted to, oh yeah, sorry, I missed that one. Yeah, so I guess one of my leaving questions is, will we still be here 3 million years from now, or will we just be some footprints in the volcanic ash? Thank you.
Thank you very much for these. Right, do we have any questions? If you have a question in the room, please put up your hand and somebody will come around with a. We have a question at the front here.
A few years ago, I was working on diffusion chronometry. And the idea then was, in theory, you could predict for any particular volcano the time span between seismic events and actual eruption. Is that true, and is it practical?
I know that for some, because now they're trying to do more where you link exactly that, so you can do kind of fast analysis and try to see how is the timescale between the seismic, and does that responding to magma influx, and is that when then you can track it and then there's an eruption. And it does work in a lot of cases now, but I think for like these systems that are long-lived with sporadic, we just don't know enough yet, because they're not erupting. I think they did it for La Palma. I think it was successful. I know for Hawaii, I think it's been done. So I think the trouble for the interplay, especially for Australia, it might be a long time before the next one. We just don't know. So doing that real-time monitoring is definitely where things are moving, but there's still a lot of work to be done.
We have a question online from Neil Baker. They ask, could the two geographically separated active volcanic intraplate loci, i.e. Victoria and Queensland, within the Australian plate potentially be representative of either end of an incipient rift, or are they otherwise related in terms of mantle activity, for example?
Yeah, it's a really good question, actually, and I don't think we have a consensus in the geological community either. So in Australia, is being classified traditionally as these central volcanoes, these really large volcanoes, and then the volcanic fields. And the central ones are thought to have been related to hotspot volcanism, but actually even that's been questioned these days. But there are thought to be controls so where you've got differences in thicknesses in the lithosphere, so you have different, then you get kind of like these little upwellings of mantle to lower pressure, so it starts to melt. So there's a lot of debate still about what actually is the cause of volcanism in Australia. So I actually had 2 slides kind of explaining it, but I didn't go into it in my talk because there's just so much debate. But it can be that there's different lithospheric structures, and it's supposed to be as you shear in the asthenosphere over it, it can kind of erode bits off. People talk about former subducted slabs, and that's providing the fluids that then have enriched the mantle nearby, which makes it, when you just move it up a little bit to a lower pressure, is ready to melt. And the relationship between the rifting in the Coral Sea in the north or the opening of the Tasman Sea in the south is not 100% sure exactly what that role is at the moment. So hopefully that answered that question.
Great, thank you.
Another question over here. Keith.
When I visited Vesuvius many years ago, we had a little talk beforehand, and they went on about how they've got sensors all around the place to predict if it's likely to happen again. And then, a few weeks ago, Mount Etna erupted quite vigorously. I mean, do they have sensors there that really can predict if it's likely to happen?
Yeah, so I guess they're relying on that. They're monitoring, obviously now you can monitor from the ground and you can monitor from space. And so they're looking at inflation. So is there any upwelling of the land surface? And it can be detected by very small degrees. They're definitely well monitored with seismic stations. And so if there is influx of new magma, so coming through, that is expected to create seismic activity, so earthquakes, which would be detected. Whether or not then that would lead to a volcanic eruption or not is sometimes a bit of a grey ground. But I think, yeah, in Vesuvius, Campi Flegrei, for example, is a fascinating case study. You know, there's so many people in Naples, between Vesuvius and Campi Flegrei. And I think the eruption warning to Campi Flegrei is based upon kind of a middle of the road, most probable eruption. But we know there's been much larger activity in the past. And they've tried to do evacuation plans where I think they have to evacuate something like 500,000 people in 72 hours. It's something like that. And I think when they try to do a run through, only 1,500, 1,600 people turned up. And the one thing that strikes me is when I read accounts from Tambora, and the account says that when somebody held up their hand, they couldn't see their hand because obviously the ash is that thick. You just think, if you've got signs to where to go, or you're assuming that the rail network's not going to be disrupted by earthquakes, you know, it's actually it's incredibly scary thought to think, how actually are you going to get somebody out of that situation when and if it happens next time at either, I guess, at either of those volcanoes, with the population now that you've got in that region.
Another question.
My question is, how concerned are geologists with the Yellowstone dome?
Yeah, I think, I mean, I can only speak for myself, but I know that the USGS do a lot of communication on that topic, because it seems to be one of the, you know, it always makes the headlines. Yellowstone's going to blow. And as far as I remember, well, I think they have a very good web page for Q&As on this, so I would send you to that site. But I think, you know, it's these larger scale systems that operate on much longer time frames. I personally would be much more concerned about where a volcanic explosivity 7, not an 8, where and Yellowstone has had smaller eruptions, of course, so the next eruption at Yellowstone might not be a large, massive super volcanic eruption. It could be even a smaller one. But the ones I would worry about, the ones that on average happen more frequently, which would be that next size down. And so I have a postdoc who's working on global volcanic risk from volcanic explosive 7 size events at the moment.
We have a microphone.
When you have a swarm of smaller volcanoes, do you feel that's more like a pressure cooker letting off steam, and you're less likely to have a supervolcano like Yellowstone?
It really just depends on the volcano. So in the volcanic fields, they're usually, it's just that the magma supply in that area is very small. So in that area, a small amount of magma would come up, and then the system likely freezes because there's no connected supply. Now, there are volcanoes that do seem to have patterns between larger scale eruptions and then smaller ones, and they seem to alternate. So I had a PhD student who was working on Kelut in Indonesia, and there it did seem that you would, and a lot of other ones, you've got a dome forming eruption, which is kind of an effusive. It's not an explosive event. It's just forms this plug in the crater, but then that can, when it does collapse, it can decompress quite a lot, and then it leads to this larger volcanic explosive eruption the next time. So it does, volcanic behavior obviously does vary a lot, and there's certain things that we do have patterns, but then of course they just surprise us. Like if you get the Kingdom of Tonga eruption, that one was actually not a large amount of magma or not a large eruption, but had a massive impact, likely because it was submarine, and the water that ingressed actually into the system made it then really much more powerful and explosive than we could have imagined. So it's, yeah, it's sometimes hard to tell.
So, thanks for sharing this story about the tsunami and how people knew when or how when to get away from it. Can you share other kind of stories that you've come across, yeah, from traditional law?
Yeah, so there was another, I think can't remember the name of the island, but I think it was one of the Andaman Islands, and it was same. So they were only a very short distance away from the earthquake, and then 100 years ago, I think they'd had another one. So within the community, there were all traditions that if the sea was, that one was if the ground was shaking. So if the ground was shaking, then they had to get to higher land. And I think they only had 10 minutes between when the earthquake happened and the wave reached the island. And it was miraculous that something like out of 70,000 or so people, there was only 7 fatalities when they literally had 10 minutes to get out of the way. But yeah, there's many examples of I think across like Papua New Guinea as well. I think there was another example there about tsunami where they had the traditional knowledge and it helped.
I think we've got time for one more question. If there's one more question in the room or online. Okay, well, Heather, thank you very much indeed. So the next public lecture will take place on the 26th of August, where Dr. Lucia Paredes will be presenting Lost in Illustration, the Art and Science of Communicating Through Graphics, and registrations will be open online very soon. Please join us if you can in the lower library for drinks and conversation. And thank you for coming, and hope to see you next time.